Okay, so welcome to 10.418, 618. Today we're going to think about a very different way of talking about parameter estimation from presumably what you're used to. That new way of thinking is going to be that of the Bayesian approach to parameter estimation. And in order to do that, we're going to look at two small case studies. One is the naive Bayes model that hopefully most of you have seen before. And the other is latent Dirichlet allocation, which is going to be a new example of a topic model. And so homework 3, you guys will be wrapping up on Wednesday. And then in homework 4, you'll actually be implementing a topic model. But a rather modern variant of it. So today we'll be talking about kind of a classic variant of, or the sort of classic latent Dirichlet allocation model. In homework 4, you'll kind of be doing a modern version of it. Okay, so what is topic modeling? Well, the motivation is that you could imagine being given a massive corpus, and you're asked to carry out the following tasks. Okay, so organize all of the documents into thematic categories. Maybe describe the evolution of those categories over time. And enable a domain expert to actually go in and analyze and understand what's in the content. And then find relationships between the categories and understand how authorship influences the content. And all you're given are documents, right? Maybe historical documents, and maybe they're in some language that you don't even speak. And so what you're trying to do is build a system that you can hand off to some expert who's going to be able to interpret the output of your system in some meaningful way that will give them insight into what is sitting inside that massive collection of documents. Okay. So we say that topic modeling is a method of sort of mostly or usually unsupervised discovery of latent or hidden structure in a corpus. And that it's applied primarily to text corpora, probably because that's easiest, but the techniques are actually more general, and so they've been applied to other things like computer vision problems and computational biology problems. And so really, topic modeling is providing a toolbox for modeling, and it's prompted sort of the exploration of a variety of new inference methods and methods for accommodating really large-scale data sets. Okay, so when we talk about topics, what we mean are sort of ways of describing these thematic categories that appear. And so, so this is actually topics drawn from one of the models of the variety that we'll talk about today. But when run on a corpus of machine learning papers from a conference called NeurIPS. Oh, sorry, this is the maybe ICML, the International Conference on Machine Learning. And so you can see kind of what's happening here is the first topic here. What I'm doing is I'm displaying the words that are high probability under this topic. Okay? And so you can see that things like convex optimization, semi-definite programming, constraints, max margin. So this seems to be kind of an optimization topic. Okay? Down here is a whole collection of words or phrases that are all kind of related to decision trees. So like something like random forests is sort of an ensemble method for it. And then the last section here is a topic on approximate inference. So there's a bunch of things that you probably don't yet recognize, like variational Bayesian or variational inference. Those are what we'll talk about next. But there's familiar things like Markov chains and Gibbs sampling and MCMC, so on. Okay. So you could also imagine using the information that you extract from the corpus to build sort of a map of the actual relations between documents. And so this is actually a map of National Institute of Health grants, like successful grant proposals. And you can kind of see that the ways that they actually fit together in this map are tied to the actual content of the document. So these labels were actually kind of applied retroactively. And you can then kind of see how you get these sort of clusters. You could also apply this to image data and actually learn to sort of spatially segment the data that way. And so broadly, these methods are going to apply in settings where you have some data that you want to infer latent structure about. Okay, so to get to latent Dirichlet allocation, we're going to step through some sort of precursor models and then get to the actual main model. Okay, so this section I'm really going to lead up to a discussion of Bayesian inference for naive Bayes. But I'm going to be doing it in slightly different terminology than maybe what you're used to. Okay, so first I want to talk about the Beta-Bernoulli model. And so to do that, we need to know what the beta distribution is. So this is the probability density function for the beta distribution. Okay. And it tells us that the density of a particular point estimate phi conditioned on parameters, alpha and beta, is given by 1 over the beta function of alpha beta times, so this is just some constant, times x raised to the power alpha minus 1 times 1 minus x raised to the power beta minus 1. And for different values, so to be clear here, phi can range over values 0 to 1. And so we can actually plot this density function for different values of alpha and beta. Okay, so if both alpha and beta are 0.5, then you get a completely uninteresting uniform distribution. Okay, so that's this one. Or maybe that's sorry, that's this one. Alpha and beta equal to 1.0. Okay, so in that case, you get an exponent of 0 for both of these. You're just raising the value to the power 0. So completely uninteresting. You could also have a distribution like this 0.5 one, and that would give you this sort of U-shaped density. If you have values of, say, 10 and 0.5, it's going to have a slightly skewed distribution that puts a lot of probability mass on something like 0.7. So lots of different possible distributions all from this family. Okay, so the Beta-Bernoulli model is described by the following generative process. So a generative story is just a way of articulating the full content of a Bayesian network. Okay. So this is more specific than a Bayesian network would be because it's actually telling us what the distributions are. So you could think of this as providing a distribution over coin flips. And the way that we're going to get it is we're going to first draw the weight of a single coin. Okay? So take this beta distribution, okay, and draw one parameter phi from it. Let's suppose we picked alpha equal to 10, beta equal to 5. Then we would be sampling from this tall distribution here. So it's this blue one. And with high probability, phi is going to come up in that like 0.6 to 0.8 range. Okay, so we sample phi, and maybe we get back that phi is equal to 0.8. Okay, now we're going to generate a corpus of length n. Okay, so we have n coin flips, and for each one, we're going to use a Bernoulli distribution, right? So how do we take a sample from a Bernoulli distribution with parameter phi? Well, we just flip a coin with weight 0.8. And with weight 0.8, it comes up heads, and with weight 0.2, it comes up tails. So we flip it a bunch of times, and that gives us 10 different samples from this beta Bernoulli model. Okay, so here's the Dirichlet distribution, and it's actually the same as the beta distribution when you're in 2 dimensions. So here, this is just the same slide, except I changed the word beta to Dirichlet. Okay. But it generalizes to the multidimensional case, and that's what we care about. So the beta distribution, which is a special case of the Dirichlet, is useful if you want the parameters of a Bernoulli distribution, right? Because it's giving you back a number between 0 and 1. The Dirichlet is useful if you want, say, the parameters of a multinomial distribution, meaning that you're going to now have a vector phi of parameters that sum to 1. Okay? So here we have the vector phi is in Rk, and each phi j is in the range 0 to 1. And further, we have this property that the sum from, say, little k up to capital K of phi k is equal to 1. Okay. So this Dirichlet distribution is just 1 over that beta function times the product of phi k raised to the power alpha k minus 1. Okay. And what we get back is this vector that could function like, say, the weights on a k-sided die. Right? It's telling us an actual probability distribution over the sides. Okay, so the Dirichlet multinomial model says, let's sample a parameter phi from a Dirichlet over beta, parameterized by beta. Okay, and that's going to give us back some vector of phi 1, phi 2, all the way up to phi k. And then we're going to sample words from this model by saying for each word, sample from a multinomial distribution with parameters phi. Okay, does anyone remember why I wrote multinomial 1 phi here? So xn is in is from the set 1, 2, up to k here. What are the parameters of a multinomial usually? Just remember this. So one of them is this phi distribution that tells you the probability of getting each of the sides of a k-sided die. What's the other parameter?
Weight of each of the individual.
So the phi is the actual weight of the individual classes. So what does 1 tell us?
Is it like the partition function, like the sum?
Not quite. It's something even simpler than that. So the multinomial distribution, in general, is giving us a distribution over counts of many rolls of a k-sided die. Okay, so if I had written multinomial n phi, that would mean we want a distribution over the number of times that each class comes up if I roll a die n times. Okay. So here we're saying independently you should sample 1 dice roll at a time. So a multinomial with just 1 is of that variety. Okay, so we can think about the Dirichlet multinomial distribution as providing us with just a distribution over a single corpus of, say, words, where you have a vocabulary of size k. Okay, so here it looks like I have a very uninteresting vocabulary. Maybe there's 4 or 5 different words in my vocabulary, and so that's why it looks like it does. Okay, so what we can think about now is a different generative story for the Dirichlet multinomial mixture model. Okay, so this is different because now we're going to say for each document and of, say, a set of M documents, we're going to draw a topic for that document. Okay, you could think of this as like a label of what that document is about. Sports, movies, history, politics, whatever, what have you. Okay. And then for each word in the document, we're going to sample the word from another multinomial distribution, but this time where the phi distribution is actually selected based on whatever topic we just chose. Okay, so let's think about now where the parameters are coming from. So the distribution over topics is just coming from a Dirichlet distribution over the vector theta. So theta are the parameters for the distribution over topics, whereas here we're going to say that this phi distribution is, we're going to sample one phi distribution for each of the topics. Okay, so phi, this is actually a vector, right? We're sampling the entire vector phi k, one for each of the different topics.
Question. Shouldn't Dirichlet be, the parameters should be alpha and beta? Or does it just take one?
So it takes one vector. So whenever let's go back to this real quick. So the beta distribution has scalar parameters alpha and beta. The Dirichlet distribution, in its general form, has a vector alpha. So this is a vector of alpha 1, alpha 2, all the way up to alpha k. And the restriction on the alphas is that each alpha j is greater than 0. Okay, so you could think of the alphas as essentially giving us sort of weights for the different classes. And so here we can actually visualize the Dirichlet for 3 different values of alpha in just this 2-dimensional space. So what we're looking at here is the probability of the vector phi for phi 1 and phi 2, but also for phi 3, because phi 3 is just equal to 1 minus phi 1 minus phi 2, right? Because we just said that the parameters phi sum up to 1. So if you know what phi 1 and phi 2 are, then you know what phi 3 is. So that's why we're only seeing this triangle here of different values of phi, because values over here would add up to greater than 1. So we can't have those. Okay, so you could, depending on what you choose for alpha, if you put all of the alphas as, say, values greater than 1, say they were all equal to, say, 5, you'd get a plot that looks something like this. It's kind of concentrating the probability mass in the center. Whereas if they were all small values between 0 and 1, you could get kind of this bowl shape that's trying to push the probability mass to the corners. Okay, so this is sort of our first generative process, and you could think of this as you could think of this in 2 ways. One is where the corpus that you're going to work with is just these words, right? So you have document 1, document 2, document 3, and you generate, some collection of words for each document. Okay? And in this case, I actually allow the number of words per document to vary, n sub m, right? It's specific to the document. So that's why this one can have 4 words and this one only has 3 words. Now, we're going to be working in a setting where you learn from just data that looks like this. We're not going to actually observe the topic z. But you could, right? You could say, okay, there's also a value z1 here corresponding to the first topic. And this is, say, equal to sports. This document doesn't look like it's about sports, but it's possible. And then z2 here is about politics. And z3 is also about sports. Okay. So in our setting, we're going to be looking at settings where these are latent topics, but I also want to think about the case where they're observed. Okay, so the reason I want to think about the case where they're observed is what I just drew up there on the slide was actually an example of naive Bayes. Okay. So, namely, what I just said was that we have documents, and they have labels, right? And then we have features for documents, like the contents of the document. Right? And I gave a particular instantiation of naive Bayes here, where we're saying, Zm is the actual label for the document, and then the x vector, x sub m, is the vector of words for the document. Okay. So let's think about naive Bayes for a second here. So the first point that we want to make is, so this would rightfully be titled Bayesian naive Bayes. Okay, so the whole point of naming it that is that the standard naive Bayes presentation does not use Bayesian inference. Okay. So what is Bayesian inference? Bayesian inference is going to say that suppose you are given data. Let's call it D. Your goal is to learn the posterior distribution over the parameters theta given D. So what do I mean by that? I mean the goal is actually to learn P of theta given D and to figure out what that is. This is very different than what you're used to doing. Okay, so what are you used to doing? The standard setup is, let's actually be clear about sort of what our model is. So our model here is this Dirichlet multinomial. So we're saying we have parameters theta that are sampled from a, make sure I get this right. So we want okay. I just want to stick with the right notation. Theta, alpha, phi is beta. Okay, so we're going to say we have theta, which is sampled from a Dirichlet parameter as by alpha, and then we have phi sub k, so that's another vector, which is sampled from a Dirichlet parameter as by beta. for all k. Okay. And then we're saying that we have a particular z, you could think of this as like a zi, is sampled from a multinomial, or if we prefer, we could say a categorical distribution parameterized by theta. And a categorical distribution is just a multinomial with n equal to 1. And then the vector xi is sampled from a categorical with parameters phi sub zi. And this is for all I. So, okay, so how do we usually do data? Well, maximum likelihood estimation. So, this is option 1 here, would say that the way that we should learn parameters is by maximizing likelihood. So we should find theta and phi, you can put little hats on them, that are the parameters which maximize the joint likelihood of the entire data set. So that would be the probability of the data given theta and phi. Right? And if I asked you to, you would be able to write out that distribution over the data given the assumptions of the naive Bayes model. Okay. And, oh, sorry, there's an important detail that I need to fix here. So we have to have this inner for loop over features, or else we'd only have one feature. So here we could say for feature and we want to say capital M, we'll sample that nth feature from a categorical. And then we do this for every training example. Right, so the whole point here is just that that xi is a single feature or a single word in our document. All right. So, okay, so one way that we can learn is by maximizing the likelihood of the data and picking the parameters that maximize that likelihood. And so what would we actually get back if we maximize the likelihood of the data? Like how would we solve this maximization problem for just a standard naive Bayes?
Counting?
Yeah, we would just do counting. Solve by counting. And you'll notice that we have successfully, if you want to call it that, ignored the priors over the parameters. So we actually have these prior distributions over the parameters. They say that they came from a Dirichlet distribution. Okay, but we completely ignored them here. We've just described the likelihood of the data D given phi and theta. Right, so here let's say that D is a collection of Zi, Xi pairs, right? Your training data. I equals 1 up to n. Okay, so so this is sort of silly, so can we do something better? Well, yeah, we could do better. We could not ignore the prior over the parameters. So that would be map estimation. And if we're doing map estimation, then we pick theta hat and phi hat to be the argmax over possible thetas and phis, where we maximize now the posterior over theta and phi given D. So this posterior distribution, by Bayes' rule, is equal to, actually, can someone apply Bayes' rule to this here for me? Yeah.
Probability of D given theta and phi.
Okay.
Multiply with probability of probability of theta and phi.
Good. And there's going to be one more term here. So this top thing that we just wrote here, this is the joint of P of D, theta, and phi. So how do we get it to be this this conditional where we're conditioning on D?
Also divided by probability of theta.
Right. Okay. So so with this in mind, we can now say that this P of D is not a function of the parameters. And so we can rewrite this as argmax theta phi of P of D given theta times theta and phi times P of theta and phi. Okay, so this is a little bit better. And in fact, we still solve by counting. And now it actually takes our priors into account, right? So I think the map estimates of the parameters here should be something like theta hat sub k. So the kth value of theta is going to be alpha minus 1 plus sum over all of our training examples. So I equals 1 up to n. We're going to have these indicators that are just saying, is zi equal to k? Oh, and that's not with equality. We would need a partition function if we were doing it this way. So we could just say that, you know, the actual parameter is proportional to this. So the way that you would compute it is compute all of these values and then just normalize the vector theta. Okay. And then similarly, map inference for phi would give you that phi sub k comma, let's say we index word types by w, is going to be proportional to beta minus 1 plus, now we need to sum over all of the training examples, I equals 1 to n, sum over all of the feature vectors, so this is m equals 1 to m, and take the indicator of whether or not the actual value of xim is equal to w, and the indicator of whether zi is equal to k. So here, we're just counting up all of the cases where the word is the wth word and the topic is the kth topic, or the kth label. Okay, so far, really all we're doing is sort of review, right? So where does Bayesian inference come in here? So Bayesian inference, let me make one more statement here, which is, so if we wanted to do inference with these point estimates of the parameters, then what we mean is, suppose you want a distribution, so suppose you're given a new x, okay? Then you can actually estimate the probability of, say, z equaling some particular k, given that x and the parameters theta hat, and phi hat. Oh, sorry, so to be clear here, point estimates and point estimates refers to the parameters. So point estimates of the parameters would be like the actual vector theta hat and the actual matrix phi hat. That's what we mean by this. So if you were to do this, right, this would just be given by the naive Bayes model, right? What's the naive Bayes model? Oh, it's just the thing that we didn't even bother writing down. Probability of probability of z equaling k given theta hat times a product from m equals 1 up to capital M of the probability of xm given z and phi. So here, this distribution is just going to be the usual distribution given by a naive Bayes model, right? This is the part where this is sort of the actual naive assumption of naive Bayes. Okay. So now, suppose instead you wanted to do Bayesian posteriors or Bayesian parameter estimation. So what we do here is we say that what we're after is a distribution over the actual parameters themselves. Okay. So what we want is the probability of theta given all of our training data D, okay, which really just amounts to all of the z's. So we don't actually need it to depend on all of the x's. It's actually only going to depend on the d's. And then the other one that we want is the probability distribution over phi given d. Okay, so think about what it is that I'm actually asking for here. What I'm asking for is a distribution over real valued vectors, theta, and real valued vectors phi k. And the question is, what is the form of that distribution? Okay, so here's where things get interesting. So it turns out that the Dirichlet distribution is conjugate to the multinomial distribution. Okay, what does this mean? It means that the posterior, okay, so now I'm going to change, the notation on the slide is going to change just to be sort of for the general case here. So here we're going to have 1 phi, and then we're going to sample a bunch of independent x's from that phi. And so what we want is the posterior p of phi given x. Okay, so by Bayes' rule, we have p of x given phi times p of phi divided by p of x. So now let's define a count vector n such that the entry nt denotes the number of times word t appeared in your sample. Okay, so here's the punchline. The posterior p of phi given x is also a Dirichlet distribution. The parameters of that Dirichlet are the hyperparameters beta plus that count vector n. Okay, so then the question would be, why does this happen? Like, why is it that the posterior of this thing is a Dirichlet distribution? Okay, so let's actually go backwards. Let's first look at what the consequent, oh yeah, question.
So on the slide, you're first sampling words from a Dirichlet distribution, right?
Yep.
And
Or no,
then,
I'm sampling a single vector once from a Dirichlet distribution.
but then your words xn are kind of dependent on that.
Exactly, exactly.
So you're sampling from a given distribution, then you're trying to predict that distribution, right?
Yes.
So why is that a surprise that it is a Dirichlet distribution?
So if instead I had sampled parameters phi from a Dirichlet distribution, and then I had somehow used those as the mean of a Gaussian and sampled a bunch of x's from a Gaussian, the posterior over phi would not be a Dirichlet distribution. In fact, I have no idea what it would be. I don't think it would be any like distribution that we have a name for. Could you jot down that we should probably have on the homework a question that asks them to show that something is not conjugate? Yeah, thanks. That's a great, great question. Okay, so we'll have you keep thinking about that on the homework. So here, the point is that I picked this pair of distributions because they have this property. Most of the times, when you multiply, I mean, like what I'm getting at is that here we multiplied together this multinomial distribution with this Dirichlet distribution. And for some reason, it worked out that the posterior ended up also being Dirichlet. Okay, so let's actually look at this particular pair of distributions and see why it is that that works out, because it doesn't usually. Okay, so what we need here is, say, sort of be a little Dirichlet multinomial conjugacy. Okay, so what we want to say here is we're after the posterior, okay, of phi given our data d. Oh, and let's actually match the slide here. So I think on the slide it had beta. So we're going to use that beta as our hyperparameters. So we want a distribution over phi given our data and our hyperparameters. Okay, so what that looks like is we're going to have a bunch of terms here. So the first term is going to be, so this is, this probability is, let's say, proportional to, so I'm going to drop the probability of the data term because it doesn't depend on phi. So it's proportional to the probability of the data given the vector phi. Oh, and sorry, so here the data we just said was this vector of x's, so we'll use that notation. Times this prior distribution over phi. And so this is equal to a product from I equals 1 to n of the probability of each individual xi given phi times the prior of the Dirichlet. So what do these look like? Well, the first of them, or let's do this this prior first. So the prior here is going to be proportional to a product from k equals 1 to capital K, where for each one we take phi k and raise it to the power beta minus 1, or beta k minus 1. So what I'm leaving out is there's this extra 1 over the beta function term, but it's a constant with respect to phi. So we don't actually need it here. Or sorry, with respect to the hyperparameters. So that's our prior term. And now let's get our likelihood term. So our likelihood term is going to be a product from I equals 1 to n, and a product from k equals 1 to capital K, where for each one we're going to have phi sub k raised to the power And this is the fun part. This is just going to be a little indicator as to whether xi is equal to k. So what we're essentially doing is we're saying multiply together all of the phi k's, raising only one of them to the power 1. That's the one for which xi is equal to k, and all of the other ones raised to the power 0. So what does this give us? Well, what we can do now is we can actually simplify this whole expression because it's actually equal to a product from k equals 1 to capital K, where we multiply together a bunch of phi k terms and raise them to the power beta k minus 1 plus a summation from I equals 1 to n of these little indicators, counting up how many times xi was equal to k. Okay. So all we did was observe the fact that if you multiply these together, you get this summation in the product, and then I just combine the two. Sorry, this summation in the exponent. And then I combined the two exponents by addition. So this whole thing means that p of phi given x and beta follows a Dirichlet with parameters vector beta minus 1, oh not minus 1, the minus 1 is inherent. It's beta plus some count vector n, where the say, what did we say? The tth entry, or rather the kth entry in n is the number of times that some xi was equal to k. Oops. Okay, so the fact that this worked out is like practically a miracle. Okay, it's not entirely a miracle. There's a good many pairs of distributions that have what we call conjugate priors. So we actually say that the Dirichlet is the conjugate prior of the multinomial. Okay, so now let's go back to Bayesian parameter estimation here. So we said Bayesian parameter estimation is going to tell us that this distribution, P of theta given D, is actually given by a Dirichlet where its parameters are, so it's a Dirichlet distribution. We could write this like a Dirichlet over theta given hyperparameters alpha prime, and this is a Dirichlet over phi k given hyperparameters, say, beta prime k. Okay. So we just need to define the hyperparameters properly. So the hyperparameters here are going to be that alpha prime is just a count vector for, let's see, the original alpha vector plus, just make sure I get good notation here. So actually, let me do it a slightly different way. So rather than defining the whole vector, let's define one element at a time. So alpha prime k is alpha k, which was the original hyperparameter, plus the indicators. So this is going to be an indicator for how many times did zi equal k. And then beta kw prime, not a vector, is going to be the original beta kw plus a sum from I equals 1 to n, and another sum from k equals 1 to k of the number of times that word xi was equal to w times the number of times that zi was equal to k. Okay, we're almost there. We need to do one last thing, which is that before, with map estimation, we said, okay, you get back a single set of parameter values, and then you do inference with those point estimates just by multiplying some numbers together. Okay, so what if you just got back two probability distributions over the parameters? Okay, then what you need to do is Bayesian inference for prediction. So what would that look like? It would look like you're trying to basically estimate the probability of some z. So here, let's again, as before, we're given some new x and distributions p of theta given d and p of phi k given d. And so now, what do we want to estimate? We want to estimate the probability of z given x and the hyperparameters, which are just the alpha prime and the beta prime. And if we do that, what would we find? Well, we would find that this distribution, p of z given x, is obtained by marginalizing over all the possible values of theta and phi for the joint distribution, p of z given x, theta, phi. Oh dear. This integral looks really bad. We just set up an integral here where we're integrating over this vector theta, this matrix phi, and we're now trying to sum over all the possible values of those real value vectors just so we can get a distribution over the topics. Okay. So how on earth could we estimate p of z given x and alpha prime and beta prime? Any thoughts? What tools do you have in your arsenal to estimate a distribution like this? That just looks like, you know, some mess of an integral.
Like give something.
Yeah, why not? So sample any z's from some favorite Markov chain Monte Carlo method. Okay, so this is what it means to be a Bayesian. Naive Bayes has nothing to do with being Bayesian. The name naive Bayes is just because we make this naive independence assumption in our application after we apply the Bayes rule. Okay, the fact that the name Bayes shows up in naive Bayes is just sort of confusing. Here, we're actually now being Bayesian in the sense that we are expressing our uncertainty about the distribution over the model parameters. Okay, and what's left here is a totally, a fundamentally different way about thinking, or a fundamentally different way of thinking about parameter estimation, right? At any given moment, you don't just have a single value for your parameters, you actually have a full distribution over them. Okay, so I guess I should add that, maybe if sampling didn't work, or if it didn't work very well, it's possible that sometimes can be solved analytically. Meaning, we could just do some more math, and maybe we could actually work out exactly what that posterior could be. I actually didn't do the math, and as far as I know, like nobody actually uses Bayesian inference for naive Bayes. Like the whole reason that you use naive Bayes is because like it's incredibly easy to implement. You just do some counting. Like it's just not made for like your average person who knows how to do this math, right? Anyway, I'm not sure if this works out analytically. It feels like it should because we have all this conjugacy going on. So we could probably solve it analytically. That would actually be a great homework problem. Do you want to write that down too? Okay, so what we have here is this new framework that we can work with, and now we can talk about latent Dirichlet allocation. Okay? And so in the past, when teaching LDA, I've made the mistake of not stopping to do this obnoxiously technical discussion of naive Bayes, right? Hopefully this is the most obnoxious presentation of naive Bayes that you have ever seen, right? Mostly like we just like do some simple counting, right? Here we're actually like making things essentially more complicated for ourselves by thinking in this Bayesian setting, okay? So I'm not actually advocating for you to ever actually use Bayesian. Well, maybe this might actually work better than regular naive Bayes, but I'm not really advocating for it. Instead, I think it's an incredibly important pedagogical step towards understanding what's going on in latent Dirichlet allocation. Okay, and here's why. Because naive Bayes is a mixture model. This, I still haven't solved this stupid font problem. And so on the top, we're looking at a mixture model, which is where you pick a particular topic for a document, right? Like you say, this document is going to be all red words. And then you sample a bunch of red words. And then you say, okay, now let's take a new topic and let's sample a blue word and then a yellow topic and let's sample yellow words from that. And an admixture model does something different. It says, okay, let's actually have each document be a mixture of multiple topics. So our first document is going to be, 1/3 red, 1/3 yellow, 1/3 blue. And then our second document is going to be mostly red with a small probability of being yellow or blue, and so on down the line. And so we're now going to think about a different generative process that could give rise to this same collection of documents, but through different latent structure. Here's what it looks like. It's almost the same as that Dirichlet multinomial mixture model that we had, except that we sort of pushed two things inside this document, further into the for loops. So what we're saying is, for each topic, we're going to sample a distribution over words. That's phi k. Okay, and so what that you could conceptually think of that as is think of those topics from the ICML database work, right? One of the topics might be a distribution over things that seem to be about decision trees. Another topic might be things that are about convex optimization. Okay? So those are our different topic distributions over words. And then for each document, we're going to sample a distribution over the topics. And then for each word, we're going to sample a topic assignment and also a word. And the interesting bit is you sample that topic assignment, but then the distribution over words that you choose is dependent on whatever the topic assignment for that word is. Okay? So here's what's weird about this. We're not saying that a document is about a single topic. We're saying that if you want to describe a document, you actually need a distribution over topics for that document. Okay, so here's how this could work. So the generative story is going to begin with only a Dirichlet prior over the actual topics. And each topic is defined as a multinomial distribution over the vocabulary. Okay, so here's our Dirichlet prior. And now I sample one multinomial distribution. Okay, so you could think of each bar here as corresponding to one of the words in your vocabulary. And so the higher the bar, the higher the probability of that word in this particular topic. Okay, now you sample another multinomial distribution, a different one, and a different one, and a different one, so on down the line, until we have, say, 6 different topics, each one expressed as a multinomial distribution over words. And we could number them as phi 1 up to phi 6. Okay, so now we could also visualize the topic as a list of its high probability words, right? So phi 3 here, we've visualized its high probability words, and they're team, season, hockey, player, Penguins, ice, Canadian, puck, Montreal, Stanley Cup, and maybe the model picks up spellings or misspellings of words. And if you wanted to, after you knew post hoc what those high probability words were, you could pedagogically assign a label to identify the topic. Okay, but that's something you would have to manually do after the fact. So I labeled it as hockey. And I could do the same thing for each of these other distributions, right? One about Canadian government, one about hockey, one about US government, one about baseball, one about Japan. Okay. Okay, so now let's actually generate some documents. To do that, we first sample from our Dirichlet parameterized by alpha a distribution over words. Okay? So this is a multinomial distribution, a distribution over the actual topics. So this distribution only considers 6 different bars, right? One for each possible topic. So in this particular document, it seems like it's mostly going to be about Canadian government and US government. So we start sampling words, and one at a time we sample words. So the 540 boundary dispute is still unresolved in Canadian and US. Okay, so now we sample, now I want to sample the next word. So think about that generative story. First, I sample a topic assignment for the word. Okay? So I have a 6-sided die with weights according to theta 1, and I roll it, and it comes up green. So that means that the next word is going to come from the US government distribution over words. So we sample a word, it comes up Coast Guard. And then we keep going all the way through the document. And I guess in this case, I only highlighted, some of the words with their topic. But really, each word in this list should actually be highlighted with some corresponding topic. Okay, so now you want to sample your second document. Well, first you have to sample theta 2, which is the distribution over topics. And then for each word, sample a topic assignment, and then sample a word from that topic. Okay, so we just keep going down the line, and so the second document looks to be mostly about hockey. The third one seems mostly about baseball. And so you can think about this as sort of decomposing into a distribution over words, right? That's what an actual topic is. And then a distribution over topics. That's how we're representing a document, right? Okay, here's the interesting bit. Inference and learning are only going to start with the data. We're only going to observe these words. We don't know what the betas are. We don't know what those phi's are. We may or may not know what alpha and beta are. In the general case, we don't even know what they are. We're going to learn them as well. Okay? Though often, just for convenience, you just treat them as observed, like hyperparameters, because it's a little bit easier. Okay, so in order to summarize what's going on here, we need one more new concept, which is that of a plate diagram. So a plate diagram is just kind of a convenient way of writing down a graphical model. So for the Dirichlet multinomial, the plate diagram is going to have a bunch of different variables. It's going to have variables x superscript I, or let's say, I think I did xim, and then z is specific to the document I, and then we have some distribution theta. So maybe we need a little more. Oh, sorry, this is the Dirichlet multinomial mixture model. For roughly naive Bayes. And the way that we draw, oh, and then we need hyperparameter beta, some parameter vectors phi k, and hyperparameter alpha. Okay. So how can we connect all of these up in some meaningful way? Well, theta is drawn from a Dirichlet parameterized by beta. And we just have one theta. But then each of the zi's is sampled from a multinomial parameterized by theta. But there's a lot of zi's. So what we can do is draw a little box like this. Oh, that's not going to be big enough. And we can put down in the corner the number of times that we want to repeat this box. So let's say we're going to repeat it n times. One for each document. Okay. Now there's many words in a document. So the xi, oh, let's get a little more pedantic here. So phi k, these are the distributions over topics. Okay. And here there's going to be k such distributions, capital K. Right? So we can put that phi k in a box so that it gives us back capital K vectors. Okay. And then the words are sampled from Ci, but are also a function of the parameters phi k. And we need another box here that repeats this m times, if there's, say, m words in every document. So this is akin to what the regular Bayes net would look like. But essentially what we're saying here is there's a bunch of repeats of variables with lots of different indice names, right? And rather than actually writing out something like, beta, and then theta, and then document 1 is going to have Z1, and document 2 is going to have Z2. And then, right, so this is a document. And then document 1 has 3 words, X1, X2, X3. And those are a function of the parameters phi1 and phi2, which are a function of alpha. So you can see what's going wrong here. This is just becoming such a mess that to write that thing out for all of the words would just sort of become ridiculous looking. Okay? And so this plate diagram is just kind of a convenience method for collapsing all this stuff in so that we don't have to make it look like such a mess. So the plate diagram for LDA is almost the same, except that now we've moved the Z inside this inner box. So there's one topic per word. And so here what we have are Dirichlet parameters at the corners alpha and beta. We have topics. We have document-specific distributions over topics. We have topic assignments, and we have observed words. Okay. So, a couple questions. Is this a believable story for the generation of a corpus of documents? No, of course not. No, not even close, right? Like, this is a completely absurd story for where these documents actually came from, right? If I told you that all of, the history books ever written about ancient Greece were generated from this model, okay, you would just sort of shake your head at me. Of course, it's completely unreasonable, but it turns out that it might work well anyway. So why might it work well? Well, so this slide is so beautifully worded. I just copied it straight from David Bly. David Bly was one of the original authors on the LDA paper in 2003. And so here is, you can imagine him explaining to you why this absurdly simple model of documents might actually work out. Okay, so here's his thinking. So LDA is trading off between two goals. One, for each document, it's going to allocate its words to as few topics as possible. Two, for each topic, it's going to assign high probability to as few words as possible. Okay? So these two goals they're at odds, they're in tension with each other, meaning that putting a document in a single topic makes number two difficult, right? If you say that a document is drawn entirely from one topic, then it's difficult to have each topic assign high probability to as few words as possible. Okay? By contrast, putting very few words in each topic, meaning very few words with high probability, makes number one difficult, right? Because in order to cover a document's words, it actually has to assign many topics to it. Okay, so trading off these goals finds groups of tightly co-occurring words. And it's this process of finding these tightly co-occurring words that gives rise to these sort of beautifully interpretable topics. Okay, so how does this relate to my other favorite model for capturing low-dimensional representations of a corpus? Good question. So it does actually build on latent semantic analysis, if you're familiar with it. It is actually what's called a mixed membership model, which is sort of a well-studied topic. And it also does have connections back to PCA and matrix factorization. And back in 2000, it was actually independently invented. And so LDA was invented and popularized by this 2003 paper, but it was independently invented in 2000 for genetics. It's just that nobody cites that paper. Okay, so where do we go from here? What we're going to do is think about Bayesian inference for parameter estimation of the latent Dirichlet allocation model. So I'll give you a preview. If and only if we knew what all the topic assignments were. Okay, this is completely absurd. You don't ever actually know what word what topic each word is assigned to. But suppose you observed both the x's and the z's. In that case, Fully observed maximum likelihood estimation is super easy, right? This is just count and divide. We know how to do this. This is just a Bayesian network. We happen to draw it as a plate diagram, but you guys could solve this in 5 minutes, okay? If you wanted to, you could add the priors in, right? And you would still be able to solve this in, okay, maybe 10 minutes. Because again, it's just going to be sort of count and divide to come up with point estimates of the parameters, right? So when I say optimize here, what I really mean is choose the value of theta and phi that maximizes the probability of whatever you've observed. Okay? And what we're going to do is think about a setting where we take these 3 learning paradigms that we just looked at for naive Bayes, but we're going to apply it to this unsupervised learning setting, where instead of observing topics and words, we're only going to observe the words. And we're going to have to figure out everything else. And so we'll see that you could do lots of different things. You could do standard expectation maximization. You could do map expectation maximization. You could do Monte Carlo EM, which is just like expectation maximization, but where you replace exact inference over the topics with sampling, like say a Gibbs sampler. Once you're sampling, you might say to yourself, well, why don't we just do the full Bayesian thing and do exact inference directly over the parameters that we care about? Okay, we'll see that that's not going to work out, and instead we'll say, well, okay, maybe we could then sample all the parameters and the topic assignments. That actually would work out. And then we'll get a little fancier, and we'll actually integrate out the parameters, and we'll just sample the topic assignments. So essentially what we're moving towards is a setting where we can actually conceptualize everything that we just did today, Bayesian inference, but for this slightly more complex model. So that's where we'll pick up next time.